Okay, so today we're going to talk about Floodfill, which is the way that your mouse solves the maze and navigates through the maze to get to the center. And so the way that Floodfill works is first you assume that there's no walls in the maze, then you calculate the distance of each cell from the center, and you give each cell a distance to the center. So the distance of the center is 0, and then every cell out from there is +1, and then it continues +1 for each adjacent cell. And then so the overall algorithm is that you go to the neighboring cell with the smaller distance, and then you update all the distances when you discover new walls. So here's a small example. This is what it'll look like at the very beginning when you haven't discovered any walls yet. So the center has 0, and then each cell adjacent to that is 1, and then adjacent to that is 2, and so on until you get to 4 right here. This wall is always present, the wall to the right of the starting cell, so you can just like hard code that. So in this case, the mouse is right here, and then right here he moves forward 1 cell, discovers a new wall right here. Now this value of 2 is no longer valid because he cannot get to the center with just 2 moves. He has to go around the wall now. So he has to update that value to 4 here. And then that's basically how the algorithm works. And at the end of it, you'll end up with something like this. And you can see all the distances have been changed from this point. And so the way that you represent the maze in your code is going to be that each cell has a distance. So you have to have an array, a 2x2, a 2-dimensional array, 16 by 16 for a full-size maze. And each cell needs a distance, and it also needs another byte for wall info. And so, like for your wall info, you're gonna have you can basically assign individual bits to represent whether there's a wall or not a wall. So it's a 0 if there's no wall, and it's a 1 if there's a wall. And you can also have a visited bit in there also. So overall, you need 2 bytes for each cell. So when you discover a new wall, you need to update it in 2 places. The current cell plus the adjacent cell, because if each cell has 4 walls, each cell has a north wall, south wall, west wall, east wall, then like the west wall for your current cell is also the east wall of the adjacent cell. So every time you update the west wall, you got to update the east wall of the adjacent cell also. So you have to make sure that you update it in 2 places, and you keep it always consistent. And there's ways to get around that with only using, you give each cell just 2 walls, like a north, say you give it like a west wall and a south wall, and then if you want to check the north wall of the cell, you just check the south wall of the north cell. So that way you could just have one wall in each cell. Or you only have to update it in 1 place for each time you discover a wall. But if you do it this way, you won't really be able to use Green's maze generation thing for testing. So I'd recommend that you do it this way with 4 walls on each cell. And then if you use the visited bit, that allows you to do a speed run. So if you've already visited a cell, you don't need to run your Floodfill algorithm again. You know where to go and everything. And one thing you want to make is a print maze function. So it'll print the internal representation of your maze so you can see what's going on, because it's going to really be helpful for debugging. And so the way it works is you have plus signs for each post, 3 hyphens for each north and south wall, and then the pipe for east and west walls. And you got to replace them with spaces if there's no wall there. And then you can print out the star here for the visited bit, and then also you got to print the distance here. And you only have 2 spots for the distance. So if you have a 3-digit distance, like over 100, then you need to figure out some way to like cap it at 99 or something, or maybe just display the bottom 2 bits or something like that, or the bottom 2 digits. And then you also want to have an extra character here for your where your mouse is currently located. So you could use these 4 characters to say west, east, north, south.
But this is only for when you're running the simulation on your computer, right?
Well, you can. It's actually helpful to have it like on your mouse, and then
like to print it out after you've done.
Yeah, you can print it out after you've done it, or just have it on your mouse, and then you could just hold your mouse and like try to let it pretend to be that's doing this, doing the flood fill, and then you could just like print the maze each time it goes to a new cell or something like that. Or you could even like let it, if you have your Bluetooth attached, you could actually just let it go to the next cell, print the maze, and then go again. But you can't like run in real time. It has to like stop every cell in order to do that. And then so the heart of the algorithm is really like how do you update the distances. So whenever you discover the new wall, you got to run this algorithm to update all the distances. And so first step is make sure the stack is empty. You guys know what a stack is, right? Good. So you have a stack, you make sure it's empty, and then whenever you discover a new wall, you push the current cell into the stack and the adjacent cells to the new walls that you discovered. So like all those cells have, might possibly have their values changed, plus other cells, but like those are sort of like the roots of what might change. And then this part of the algorithm will possibly propagate those changes out to throughout the maze. So it's possible to update every single cell in the maze, except for the center cells. And so this part is, while the stack is not empty, you pop the top of the stack and give it the name of current cell. And then the distance of current cell should be 1 plus the minimum distance of the open neighbors. And so by open neighbors, I mean that it's an adjacent cell that has no wall in between. So if you think about it, that makes sense. Like each cell should be 1 plus the minimum of its open neighbors. So if because each time it propagates out by 1, and so your distance increases by 1. And then if this is not the case, then set it to this value and push all the open neighbors onto the stack, and then so that'll cause it to like possibly propagate the new values out to everything.
Jeremy, can you explain if there are any new walls discovered? I mean, what's the point? I think it should be
if you don't discover a wall, then there's no purpose of updating the distances because it's the same. You already assumed that there wasn't walls when you calculated it.
Oh, okay. For the current cell. Okay, do you check before you push it, and you check if this cell satisfies the rule that if it has a like smaller open neighbor cells. If it does, then
well, it will because it's right here. So once you push this onto the stack, then it'll be in the stack during this algorithm. This algorithm will run on that, so it will become the current cell, and then it would be set to the open.
So yeah, you should mention. So if it's if the satisfy rule, if it doesn't have a smaller minimum, then just do nothing, right? Otherwise, minimal plus one, then push on neighbor cells. Because if the current cell, because you push a current cell and pop a current cell, if the current cell does have a smaller open neighbor, then you don't do anything. So you don't do these things come as well. You don't do this.
Right. So I think what Green's saying is like, if your current cell is the minimum, then you don't do this. So yeah, I guess I could have like another statement.
No. I mean, if your current cell is already has a open smaller cell, if you like, if the current cell has a open and a smaller, has an open neighbor with smaller distance values compared to the current cell.
That's not what I'm saying. I think that's what I'm saying here. The distance of the current cell should be the minimum open neighbor distance plus 1.
Oh yeah.
If it is not, then we set it to that value, and push all open neighbors to the stack.
Okay.
Wait, so if it's not, you're still setting it to?
Well, it always has to be that because it always has to be that each cell is 1 plus the minimum.
So the only difference between the two is you're pushing all the neighbors onto the stack for the last case.
So this case is so there's like two cases. Like you check if it's true. If it's not true, then you do this. If it is true, then you do nothing.
Do nothing. Yeah.
Okay.
If it is true, then it's already consistent. So you don't need to do anything. And so these are just my tips for how to accomplish this. So the way that we do it is that as soon as you enter a new cell, meaning like as soon as your wheels cross onto that boundary between cells, that's when you want to run your Floodfill algorithm. So you consider yourself to be in the next cell as soon as you've entered it, and that will allow you to your IR sensors are angled so they will be able to sense the walls. Because if you're in the center of the cell, I don't know where your sensors are going to be pointing. They're going to be pointing too far forward. Another tip is to write a simulator in Visual Studio so that you can test it. And you can use Green's maze generation Excel sheet, which I'm going to show you in a little bit. And then the stack for updating the distances. We can't use dynamic memory with this because it's slow and there's just not enough memory, and you might run out of memory if you use dynamic memory. So better to just have like a static array and use that as your stack.
Okay, so it's not like actually a stack.
Yeah, it doesn't have.
Just treating an array.
It doesn't have infinite size. Like
Use fixed size and
then you just populate it and get.
Yeah, use pointer shift the position because it's the fastest way.
Yeah. And so you can use a size of 512 for that, because like you would think initially, 255 would be enough because that's how many cells there are, but it's possible to add the cell multiple times to the stack.
Because you're pushing the coordinates, you're pushing the coordinates to the stack because coordinates have x and y. So you push twice and pop twice.
No, like what I'm saying is you can add the same cell multiple times.
Oh yeah.
Because like if it's kind of basically like the way that this is similar to a depth first search. And you can do this with recursion, but recursion is like very slow. So and it uses way too much memory. So doing this with the stack method, it's kind of like depth first search. So it's gonna So like when you're doing a depth first search, you're gonna like keep adding like neighboring cells, and so it's possible to like propagate to the same cell twice. Yeah.
But that will correctly update whatever.
It'll correctly update it, but it's we account for this to happen. And then another tip is place your stack outside of any function and make it a global variable because it doesn't need to be like extern or anything, but it should be outside of the function. Because if you put it inside the function, it uses, it's called the system stack. It's different than the stack, but it's like whenever you call a function, it like allocates space for that on the system stack. And so if you have this as a local variable, it's going to allocate like a huge thing on the system stack. And the system stack is not big enough. So if you put it in if you put it in as a global variable, it puts it into a different region of memory, which has more space.
And the memory location is pre-assigned.
Yeah, it's pre-assigned.
So it's assigned at the very beginning. So whenever you stack, the system doesn't need to take extra time to like assign a new area for the stack. Like, remember for your CSS project, you like in the main search function, you create a class member function stack. Whenever you're calling this function, right?
Sure.
So you will need, the system will, spend time to allocate memory to create a stack every time. So where the global one is just like you don't need to spend this time.
Wait, what's the difference between global and local, like inside a function?
Is the global one is being created at the very, very beginning, during the initialization process.
Okay.
And
Yeah. Local only
Well,
gets called when you call the function.
yeah.
Well, okay, but I think, yeah, it gets allocated when you call the function, but it doesn't take any extra time. That's not the reason. The reason is that you run out of space when you do it on stack.
Why? Wait, why do you run out of space when it's inside the function, but not when it's global?
Because it's a different region of memory. It has more space for the global variables.
I mean, don't they both use RAM?
Yeah, but the system stack only has a small amount of space for it.
Oh, really?
Yeah. I mean, it's not the case on your desktop. If you did it on your desktop, you'd be fine to put it in the stack because it has a giant stack. But embedded systems, you have a very small system stack.
Yeah, don't use STO stack. Don't use, just make sure it's stack.
And then also don't use recursion. You could implement the algorithm with recursion, but it wastes more memory and it's slow. And it's the same reason you have a small system stack. And so recursion adds to it adds to the system stack. So.
Wait, that's to explain why you use a stack.
I'm sorry, I might be getting confused,
Uh-huh.
confusing you guys here because I'm talking about two different stacks. The stack for our algorithm is I'm just referring to that as the stack, and then the system stack, it's also a stack, but it's the stack that your program uses. All of your functions are located in that stack, and so that's the system stack, and that is a small region of memory that you have for that.
What different types of memory locations are there? What's different besides system stack?
There's the heap, but we don't ever use the heap.
Yeah.
And there's the system stack, and then there's regions for global memory, global variables, and there's regions for code.
Okay.
Yeah, those are the main ones.
And you're saying don't use recursion just in general for anything we're doing?
Yeah.
Okay.
On an embedded system, you generally want to stay away from recursion.
Good time to
Wait,
solve.
so what would you use as opposed to recursion?
You could use a stack method. You can always use a stack, you create your own stack and you can push things onto the stack.
Okay.
It's similar to so this while loop here is essentially replacing the recursion. You could do this a lot easier with recursion, I think. It's basically just a depth first search. A depth first search is super easy in recursion, but we need to use the stack method instead. And if you look at this for a while, you'll figure it out that that's actually similar to recursion. It's a depth first search. Right. Is that it? Any questions? Okay. Okay.
Wait, how does Floodfill compare to like other searching algorithms like A-star and whatnot?
A star. Not familiar with that. I think it's like the same thing. Yeah.
Any questions? Alright, we're going to give a demo
Oh, right.
of how it works. Alright, so this is an Excel file I generated with a hard code, in order to have an easy input and easy output for the wall information in a two-dimensional array. So each wall have a value of 1. Each wall have a value of 1. Each empty wall have value of 0. So this is the actual output in two-dimensional array. This indicates the row 0. This value indicates row 1. Then I add them up to make to the array. In decimal, the numbers are in decimal. So the format is like is like this. So okay, it's kind of too small. Okay, so the format because for store the wall information, because we use bit operation, we only use one bit to indicate one wall on each side. So technically we only use 4 bits on each byte to store all the walls, and plus I use 1 more bits to store the information, to visit the information for each cell if the cell get visited. So this is the format looks like. Assume this is a 1 bit with in binary form with 8 zeros, and so these are the usage for each bit. So the first one, if R means reserve, so R B. So okay, the west, south, east, and the north. So the most right bit I use it to store the if the north wall exists. The second one is the east wall, south wall, west wall. This one indicates if the cell is being visited. If it's being visited, it's 1, otherwise 0. And these 3 are reserved for some other purpose. So the value here actually only indicates the last 4 bits, and because it doesn't matter if you have these top 4 bits occupied, because when in the function you're implementing this Visual C++, you will only read the last 4 bits to display the walls.
5 bits.
Oh yeah, the last 5 bits, because you need to determine if the cell is being visited. Okay, so on the right hand screen is the exe file generated by my C++ simulation code. Even though the code was completely written in C fashion, but they're fully compatible. And I highly recommend you to write the code in Visual C++ completely by using C instead of C++, because it'll be much easier for you to migrate the code. So, because we print out a lot of things, try not to use C out, because there's no way you can use C out in the cloud. And if you just print out, you can just directly copy paste the code to your mouse without changing anything. All right, the simulation. The simulation to the right side is going to be the mouse can explore the maze exact same as we can see in the Excel file on the left. So each time I press the enter button, it displays the mouse moves for one step. So you can see here we have a top arrow indicates where the mouse locates and the current directions. So now mouse to the left bottom corner and heads up. So at the very beginning, our distance value was 0, and we manually assign value. Having the corner at 14, middle at 0, assume there's no wall, and we're going to get ready to store explore base. So I just keep press enter. Okay, see the mouse moves the first steps. The numbers unchanged because the path is now being changed significantly. Jeremy can keep explaining the rest.
Yeah, so the numbers didn't change here because you're blocked from this 12 now, but you still have this 12, so it's still 13 and 14 here. Again, they didn't change. Didn't change. Okay, now they changed. So you discovered these two walls now, and then it used to be an 8 here, but now it's a 10. So, but you can see each cell is just 1 plus the minimum neighbor. So this guy's minimum neighbor is this 9, and then this guy's minimum neighbor is the 10, and this 10 also. And then it goes 12, 13.
You can compare to previous frame. It was 9.
Yeah, it was this one was an 8 here, and then this one was a 9, and then it goes 10 and 11. Just because now it has to go down here and then back around. So the distance increase. And same thing. So you can now I've updated. Now I found that it's in a dead end because it was going to go over here to the 7. That was the only path to get out in a short distance. But it discovered a wall there, so now it's this is the highest one because it's at the end of the dead end here, and now it has to go back this way to get out. And then I found another dead end here, so now this one's 18 and it has to go back this way again.
But so when you're forced to traverse through cells you've already visited or whatnot, you just determine which cells to follow based off of how much their distance?
Yeah, you just always go to the smallest distance.
Okay.
Yeah. Or if there's 2 cells that have the same distance, say you're at this 9 and you have an 8 here and an 8 here, you can decide some algorithm to decide which one you should take.
So you can do that both when you're going to unexplored cells or cells you visited?
Yeah.
Okay.
Yeah.
So if you have all 3 open branches with same values,
Then you
and
decide.
if they're all unvisited, then probably you want to go straight first because it's faster. And however, if the front one, if they all have same value but the front one is visited, and on 2 sides are not visited, then you might want to go pick either side of them because you want to explore more cells, right?
Wait, will this algorithm map out the entire maze or just until you get to the center?
It'll just go to the center.
That makes center 0, right?
It tries to find the shortest path to the center.
Uh-huh.
I mean, it might go through the whole maze, but it can leave whole sections of the maze
Wait,
out.
so is it ever possible that where you leave out a section that could have been faster?
Yeah. So the only time that you know for sure you're doing the shortest path is when you you've run through the algorithm twice and it still went the same path.
Okay.
That's a speed run, pretty much speed run.
Wait, so how do you change your path so you look for the alternate path that you missed the first time?
Well, so you could do like what Green said, if you have 2 cells that are the same value.
That's the only thing that would cause it to differ, right? Is
Yeah.
if you found 2 cells with same values.
Yeah.
And then this time you pick.
Yeah, I mean, if you run through the algorithm like enough times and you just keep adding stuff to your maze, you will eventually find the shortest path.
Okay.
But it doesn't necessarily guarantee you'll find out the first try.
And that's because if you get to like a fork or something.
Yeah.
Okay.
So let me just like speed through this a little bit so you can see that.
Yeah, show them how it goes center, then
Yeah.
how it looks like for
Like even on the way back, it might
on
explore more
returning
stuff.
search. Yeah.
Just going around.
Wait, so to return, do you just follow like do you just go to the cell that's 1 plus whatever your current distance is?
Once you return, you keep all the wording information, but change the values.
No, I mean like how do you get back to the origin?
So what you do is you set this one to 0, and you run your same algorithm, like you update all this.
So you essentially like wipe everything?
Yeah, you change. Well, you don't wipe the wall information, but you wipe the distance information, and you set this one now as your goal, and then you just run your same algorithm again.
So are you still accepting new walls? Then?
Yes.
Yeah, you always
You search on the way back because one search from the party is not definite.
So you're just adding to your memory of walls.
Yeah, keep updating walls. Yes, because the walls are
Important.
much easier. You can generate a path without having.
Okay,
Yeah.
so now it's gonna go into the 0, and you're gonna see like all the values are gonna change. This one's gonna be 0, and then it's
Wait,
gonna
where's the mouse?
right here.
Okay, where does it wants to go?
It wants to go to the
Oh,
0.
check the left one. Compare the left one.
Huh?
See, it's the same base on left one.
Okay, yeah, I see.
So that's how much mouse explore so far.
Wait, what happened? Okay, so it's 0. It's in the goal now.
Let's keep going.
Okay, yeah. So now
It's going back.
Oh, okay.
Oh, this set that one to 0.
Oh yeah. This is my detailed searching algorithm.
Oh, so is this you're looking for where you?
It's an advanced one to like make like much more detailed. Okay, but
It's just so that you map out the entire maze.
so I generate.
So that's like where you.
I generate all the suspicious cells one
The
by
ones where they
one
had matched.
until there's no more suspicious cells. Then I set the starting point at 0.
Okay.
So it will take more time to search, but it will more likely to have search the path.
Suspicious cells and they have the same distance.
No, it's a really special algorithm. It's kind of complicated. Let me see if I can generate a.
And that's fine if we get the.
Okay. Yeah, all I need to just make for now I'm trying to search this cell. That's why I make this cell at 0.
So just imagine that as the
Yeah, once the mouse reaches that cell, it will change another cell to 0.
What do you mean by a suspicious cell?
Huh?
What do you mean by a suspicious cell?
So far, because my search algorithm, one search, the cell was suspicious. Could be a critical cell, for the fast path. So my algorithm just generate, this cell.
But that's the cell where you picked one after the other.
Yeah, I picked to check
Okay.
on the way back. So I need to go. That's why what the mouse do is trying to reach that cell first. It's my really old code. Okay, so it reached the cell. Then
Now it's going
that's just
back.
like some process. Okay, so the next suspicious cell is like here.
Okay. And then just keep going till you're out of.
Until there's no more suspicious cells.
Then it goes back to the start.
Then it goes back to start.
Okay.
Yeah.
Then you can do whatever you want.
Then you can just
Speed run.
just make a speed run. Then keep search on the way back on your speed run.
You mean like what do you mean by search? Like search a new path?
Well, once you go do your speed run, right?
Uh-huh.
You come with returns, right? You can keep searching on the way back for your second return.
You mean like a different route on your way back?
Yeah, it could potentially.
Yeah, you won't go. You may not go the same route that you came on the way back. Like you might go a different route.
It's not guaranteed to do it fast.
Because on your way here, like
Uh-huh.
you took what you thought was the shortest path,
Yeah.
but you might have discovered some walls, and then that doesn't end up being the shortest path.
Okay.
But you still continue on this path until you get to
Okay,
this.
that just saves you from having to go back and then search a new way.
Yeah,
It
yeah.
just cuts out half. of
Because
this.
for your speed run, you only generate a path with unexplored cells.
Okay, yeah.
But however,
On the way back, it doesn't matter, so you can explore.
but the faster path, but the real fast path might have some unexplored cells for now. So it's not guaranteed in the fast path until you search enough cells.
Okay.
That's why I
But
just-
although, like, theoretically, would you be speedrunning after you've pretty much mapped out the entire maze, though?
You pretty much should do speed run on the second departing.
So every time you go back? Is that what you're saying?
Okay, so very first time you search.
You search.
For
And every
both
other
party.
time
Yeah, right after starting from second departing,
you... Okay.
you do speed run, but on the way back you still do search.
Is that better than searching on your way there and then on your way back, too?
For the second one?
Because like the second run, you're not going to find anything new when you speed run.
No, you will still find new.
When you speed run?
No, not in the speed run.
Yeah,
Oh.
speed run
Go
will
the same way.
Speed run won't,
I
but
guess it doesn't matter because you get enough, as long as at the end of that, all of that, you're still gonna map it out. It'll just take a different amount of time different number of trips.
Well, he doesn't want to waste his speed run, so it's like he doesn't want to like explore on the speed
Oh.
run.
yeah, for Japan competition, you can only do 5 rounds.
Yeah, so
That includes search runs.
Yeah, yeah,
Okay, and then you just take your best time.
yeah.
and then I think at the UCLA competition last year, there was a team that they like wanted to explore like the whole maze pretty much
Oh,
on the
Kelsey,
first
yeah,
run.
yeah.
Yeah.
That's okay?
No, because
But they ran out of time. Like they
Oh.
ended up taking like 3 minutes or something, or whatever. Like,
because they were not using the stack-based searching.
Oh, so it's slow.
Yeah.
well, I mean, I think like it got close to the center, and then they decided to like keep searching because they didn't want to
Oh.
waste the run or something. But it ends up taking like they ended up taking so long.
Yeah,
That was their only run that they completed.
Their rounds are not as fast as our rounds doing curve search too. So.
So yeah, I mean, ideally, like you could like explore the entire maze your first run, just so you only waste one run doing explore.
But most competitions have a time constraint.
The what?
But most competitions have a time constraint, though. Right?
Yeah, they have a
Prevent
time
you from
constraint.
doing
Yeah, they have a time constraint and sometimes a run constraint also.
Okay.
So for
So
UCLA,
it's better to just fast run every time you start from the origin.
You want to lower your risk. Okay, so for the regional competition, there's 30 seconds penalty. As long as you pick your mouse and put back to run again, you add
You
30
can pick it
seconds.
up.
Yeah, pick up and put back and run again.
Oh.
You add 30 seconds penalty
Oh.
on your best time. So definitely, it doesn't
Well, I'm
work.
just talking about speed running it when you start.
Because on the first depart and the return, you won't have other cells you won't get searched. But if you search too much, the chance to crash is much higher.
Okay.
Unless it's extremely stable.
Okay.
So, because you want to do your first speed run as early as possible to higher rank, right?
Okay.
To secure a score. That's a
Yeah,
strategy.
yeah. Okay.
but yeah, as long as you do a search on the way back, you'll eventually discover the shortest path.
Okay.
Yeah, one return is like last year's AMC race. It took me like 3, so it took me 1 departing search plus 3 return search to get the shortest path. Because the designer was really good at this.
Wait, so theoretically, in like 5 runs, will you most likely be able to find the shortest?
Yeah.
Okay.
But you won't really run your fast speed at very beginning, right?
Yeah.
Any questions?